morning, students. Hope you all are fine and safe. Welcome back to the next lecture of Science 1. Today we will be learning the remaining topic of fourth lesson, that is effects of electric current. In previous lecture, you have learned magnetic field producing around a straight conductor and right hand thumb rule. Now let's study magnetic field produced by current in a circular loop of a conducting wire. Magnetic field due to the current in a circular coil can be understood by the following activity. Take a drawing board and fix a white paper sheet over it. Make two holes A and B in the drawing board and pass a thick copper coil through it. Connect the ends of the copper coil to a dry cell through a switch and a variable resistance. Close the circuit and plot magnetic lines of a force with the help of plotting needle. We can see that magnetic lines of force around the hole at A are in anti-clockwise direction. However, the magnetic lines of force near the center of the coil becomes almost parallel, and around the hole at B, the lines of force are in clockwise direction. In the above activity, the lines of force enter the coil from the side of the experimenter. So, we can say that the force of the coil towards the experimenter acts as south pole and the face opposite to the experimenter acts as north pole. Now, relate the above observation to the flow of current in the coil, and then we can say that if the current flows in the coil in clockwise direction facing the experimenter, then that face of the coil will act as south pole, and if the current flows in the coil in the anti-clockwise direction facing the experimenter, then that force of coil will act as north pole. The electric current in a circular loop creates a magnetic field which is more concentrated in the center of the loop than outside the loop. On examining the direction of magnitude field produced by a current carrying segment of wire shows that all part of the loop contributes magnetic field in the same direction inside the loop. Thus, we can say that a loop creates a more powerful magnetic field than a straight conductor. Now, you may wonder what happens if we change the direction. What do you see? If the direction of the current is reversed, then obviously the direction of magnetic force of lines also get reversed. So remember, due to current through a circular loop, the magnetic field lines are straight. Also, the most important thing to remember is each segment of circular loop carrying current produce magnetic field lines is in the same direction within the loop. Therefore, electric current in a circular loop creates a magnetic field which is more concentrated in the center of the loop than outside the loop. And if there are n turns in the loop, the magnetic field n times of that produced by the single loop will be created. Taking multiple loops concentrate the field into more stronger. What is it called? Solenoid. Hence, we wrap a copper wire on iron rod to make it a powerful magnet. Now let's study magnetic field due to a current in a solenoid. If a thin insulated copper wire or any other conducting wire is wound in the form of cylindrical coil whose diameter is less in comparison to the length of the coil is called a solenoid. Imagine a solenoid is passed through a horizontal cardboard such that the axis of the spiral lies at the cardboard. Sprinkle some iron filings on it. When a current is passed through it, the iron filings arrange themselves in a definite pattern as shown. A current carrying solenoid behaves like a bar magnet. A magnetic field can be increased by first increasing the current, second increasing the number of turns, and third by using soft iron bar cores. Students, always remember, if you pass an electric current through the wire, a magnetic field is created as shown. A pattern of magnetic field is similar to a bar magnet. A magnetic lines are almost parallel inside the solenoid, that is directed from south pole to north pole. But how to find the north pole and south pole of solenoid? At a circular end of a solenoid, if the current flows in anti-clockwise direction, then that end is north pole. It can be remembered with the help of symbol of anti-clockwise direction which resembles the letter capital N of alphabet. On other hand, at the circular end of solenoid, the current flows in clockwise direction, then that end is south pole. It can be resembled with the help of symbol of clockwise direction which resembles the letter S of the capital alphabet. Strength of the magnetic field inside the solenoid increases if the current I in solenoid increases. Strength of the magnetic field increases if number of turns per unit length increases. On combining the factor, we can say magnetic field is directly proportional to n times product of I. Student, always remember that the intensity of magnetic field within the solenoid is uniform. Now let's see an activity for force acting on current carrying conductor in a magnetic field. The magnetic field is so produced that it exerts a force on magnet placed near it. So, should a magnet also exerts an equal and opposite force on the conductor? Yes. Let's see how. We have taken a conductor connected to a circuit in series with a battery and plug key. The conductor is placed between the poles of a strong horseshoe magnet and it is placed such that the north pole is below so that the magnetic field direction of the magnet is vertically upward. Insert the plug key to pass the current through the conductor and observe. We can see that the conductor rod displays towards the right side. The displacement of the rod suggests that the force is acting on the conductor. Reverse the current direction by reversing the battery polarity and observe. We can see that the conductor now gets displaced towards the left, which means the direction of the force is also reversed. Now let's see what happens when we increase the supply of voltage. We can see that the conductor rod gets displaced more. The direction of the magnetic field, current and the force are acting mutually perpendicular to each other. This can be illustrated through a simple rule called Fleming's left hand rule, with the forefinger representing the direction of magnetic field, middle finger representing the direction of current flow, and the thumb point in the direction of motion force acting on the conductor. According to Fleming's left hand rule, the above experiment clearly show that a force is exerted on the current carrying conductor. The direction of this force depends on both the direction of the current and the direction of magnetic field. Now let's see Fleming's left hand rule in detail. In previous standard, you have studied about motor, but how can we determine in which direction the motor rotates? If direction of magnetic field and current is given, we will discuss one rule, that is Fleming's left hand rule, on the basis of which we can determine the direction of force. The rotating direction of armature coil for the given direction of magnetic field and current. According to this rule, if you arrange the left hand in such a way that your thumb, first finger and second finger are perpendicular to each other, and if your first finger is pointing in the direction of magnetic field, the second finger is pointing towards the current, then the thumb will give you the direction of force. Let us check how left hand rule works. Have you understood the rule? Let's see it with the help of a simple circuit. Arrange your left hand with thumb, first finger and second finger all pointing it to right angle with one another. Now point your first finger in the direction of magnetic field. Point your second finger in the direction of current. According to Fleming's left hand rule, the thumb will give the direction of force. In this case, the conductor will experience a force in upward direction or it will move up. Now, can you guess in which direction the conductor will experience a force if we reverse the direction of current? Yes, correct, in downward direction. Do you know how an electric motor works? An electric motor converts electrical energy into mechanical energy. An electric motor consists of a rectangular coil of an insulated copper wire. The coil is placed between the two poles of a magnetic field. The end of the coils are connected with two halves of a split ring. Split ring means when you cut a cylindrical ring into circular half part and it is connected in a circuit are called as split ring. The inner sides of these halves are insulated and attached to an axle. The external conducting edges touches two conducting stationary brushes. Current in the coil enters from source battery through the conducting brush, flows back to the battery through the other brush. When we apply Fleming's left hand rule to find the direction of the force on the current carrying conductor in a magnetic field, we find that the force acting on the arm AB pushes it downward, while the force acting on arm CD pushes it upward. Thus, the coil wounded free to turn around the axis rotate anti-clockwise at half rotation. Point Q make the contact with brush X and point P with brush Y. The current in the coil gets reversed and flow along the path B, C, B, A. The reverse current also reverse the force acting on the two arms AB and CD. Thus, the arm AB of the coil that was earlier pushed downward now pushed up, and the arm CD previously pushed up is now pushed down. Therefore, the coil and the axle rotate half a turn more in the same direction. The reversing of the current is repeated at each half rotation, giving rise to a continuous rotation of the coil and the axle. Commercial motors run on the same principle, but practical changes are made in their construction. Let's study electromagnetic induction. Can a magnet produce electricity? Let's explore this. Michael Faraday, the English scientist, was the first person to prove that a magnet can create current. To test this, he moves a magnet towards and away from the coil of wire connected to a galvanometer. He observed that there was deflection in the galvanometer, indicates that a current is induced in the coil. The current obtained due to the relative motion between the coil and the magnet is called induced current. The phenomena by which an EMF is induced in a conductor due to change in the magnetic field near the conductor is known as electromagnetic induction. In easy language, you can say current is produced using magnet. Let's see few experiments performed by Michael Faraday. Faraday arrived to a few conclusions by moving a bar magnet in and out of the coil of wire. Displayed here is a circular insulated wire with many turns connected to a galvanometer. Now students, observe the deflection of the galvanometer needle when the magnet is moved in and out of the coil. Different pole is introduced and number of turns of the coil is changed. Some important points to remember in this experiment is: first one, the deflection of galvanometer needle indicates the presence of current in the coil. Second one, the direction of the deflection gives the direction of flow of current. Third one, the speed of deflection gives the rate at which the current is induced. You can observe in this activity, deflection in the galvanometer indicates that the current is induced in the coil due to the relative motion between the magnet and the coil. The deflection in the galvanometer lasts as long as there is relative motion between the magnet and the coil. The deflection is more if the magnet is moved faster and less when the magnet is moved slowly. That is the rate at which the current is induced is more when the magnet is moved faster. The deflection in the galvanometer is reversed when the same pole of the magnet is moved in the opposite direction or when the opposite pole is moved in the same direction. The direction of deflection indicates the direction of flow of current. That is, the direction of flow of current can be recognized by different poles of magnet. The deflection in galvanometer changes with the change in the number of turns of the coil. More the number of turns in the greater the deflection. The magnetic field goes around each loop of wire in the coil. So if increases the number of coils, the change magnetic field is more. A bicycle dynamo is the best example to observe electromagnetic induction. Bicycle has dynamos which rubs against the tire real wheel. As the bicycle moves, a wheel on the top of dynamo turns a magnet inside a coil. This results in change in magnetic field. As a result, an EMF of current is induced. This current is carried by wires to the front and the rear lamps. Now let's study Faraday's law of electromagnetic induction. Let us take a simple coil. Let's connect one battery across it. Hence, there is a magnetic field surrounded. Let us take another coil connected across a galvanometer as shown in the figure. Now we will hold the second coil near to the first coil, more specifically to say hold the second coil under influence of magnetic field of first coil. Now we can observe that there is no voltage appear across the second coil. Now when the electric current is flowing through the solenoid coil and the solenoid coil is displaced with respect to the coil, the current is still produced in the coil. If the solenoid coil is moved towards or away from the coil, we see the deflection in the galvanometer. Also, the faster is the displacement of the solenoid, larger is the deflection of the galvanometer pointer. If the current in the solenoid coil is changed, a current is produced in the coil, or if the solenoid coil is moved towards the coil, then also a current is produced in the coil. If a current is switched on or off in the solenoid coil, a current is induced in the coil, such as induction is observed when the current in the solenoid coil is increased or decreased. Current is induced in the coil when it is moved aside from the front of the solenoid. From this experiment, it is understood that whenever the number of magnetic lines of force passing through the coil changes, the current is induced in the coil. This is known as Faraday's Law of Induction. The current produced in the coil is called the induced current. This phenomena of current induced in a coil was first observed by Michael Faraday, and he stated a law. When a conductor links with a changing magnetic flux, there is a voltage induced in it. Now let's study Fleming's right hand rule. When a conductor, such as wire, attached to a circuit and moves through a magnetic field, an electric current is induced in the wire because of electromagnetic induction. The induced current can have two possible directions in the conductor. In late 90s, John Abraham Fleming proposed a rule to find the direction of this induced current. The rule is popularly known as Fleming's right hand rule or simply right hand rule. According to this rule, we have to place our right hand in such a way that our thumb, first finger and second finger are mutually perpendicular to each other. Here, thumb is pointed in the direction of motion of the conductor. The first finger is pointed in the direction of magnetic field, that is north to south. The second finger represents the direction of the induced or generated current, that is the direction of the induced current will be the direction of conventional current from positive to negative. This rule is widely used to find out the direction of current induced in winding of a generator. Now let's see last topic of the lesson, that is electric generator or AC generator. An AC generator is an electric generator that converts mechanical energy into electrical energy in the form of alternating EMF or alternating current. Working principle of AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Construction of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft, it can be rotated rapidly. A field magnet, it may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip ring and a load, which may be a galvanometer as shown. Working of AC generator. When the armature rotates between the two poles of field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip ring and the brushes. Note the galvanometer needle swings between the negative and positive value. This means that an alternating current is flowing through a galvanometer. Direction of induced current. Initially, the armature ABCD is vertically with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature goes half the rotation clockwise, arm AB moves down while the arm CD moves up. Again, by Fleming's right hand rule, current will flow in the direction of ABCD, that is from B2 to B1 from galvanometer. Therefore, the induced current changes its direction after every half rotation and alternating current is produced. This is what is called as AC generator. Here the lesson ends. Learn and keep question number 2A. Construction and working of electric motor with neat and labeled diagram. Test for the same you will be writing on 28th August in your notebook. So students, today we have learned about magnetic field produced by current through a circular loop of a conducting wire, magnetic field due to a current in a solenoid, force acting on current carrying conductor in magnetic field, Fleming's left hand rule, electric motor, electromagnetic induction, Faraday's law of induction, Fleming's right hand rule, and electric generator. Hope you all understood the lesson. Thank you. Stay home, stay safe, stay healthy.